Okay, so we did, if you weren't here, last class we did the GoCar lab, which again, that's what the video I was showing you, kind of how that was going to go. Collected data, had our 7 to 8 data points, wide range, 2 to 3 trials each, averaged them for the times, put them into Logger Pro, and it gave us a situation where it looked kind of like maybe it was going to be linear, but then in reality, the curved best fit actually fit better than the straight or linear one for most groups. And so we found out that the shape of this graph, which we were kind of unsure of, the shape of this graph is actually an up curve as we see here. Okay. So that's important to note. If you don't have that yet, you should have that in your comp books, which is part of what the assignment was that was supposed to be submitted today. It was supposed to be a picture of the graph from graphical analysis plus your data and your sketch of the XT graph in your comp book. Now, that's supposed to be a curve. You could have used the power curve or the quadratic curve on your data to make that happen. Then we talked about this. There is this thing called a tangent to the curve, and you should write this down. This is notes. So a tangent to the curve. What exactly is it? Well, let me try to explain. It is a line, a straight line, that touches only a single point on the curve. What's the purpose? It is used to show us how steep the curve is at that point. For instance, this little blue line right here, it is a tangent. And if you notice, as I scoot it close to the curve there, it can only touch the curve at a single point. It'd be kind of like taking a straight edge and taking like a ball. It can only touch, like if I take a softball here, this straight edge can only touch the ball at a single point. Okay, so the curve that you're seeing here, again, near the bottom of the curve, it's not very steep at all. It's not very steep at all. And then as that steepness, as you roll across the ball, what happens to the steepness? Oh, look at that. It gets steeper and steeper. So it starts off with like no steepness. And as you roll the straight edge across the curved surface of the ball, you see the straight edge getting steeper and steeper and steeper. And that's what's happening on this curve right here. Okay, if I take my straight edge tool here, and go, let's go blue. Let's go with a really thin line. If I do that and I draw another one here, hopefully you see that one, again, it's just barely kissing the curve at a single point here. And let's say that point is right about there. So now it's telling me the steepness here is steeper than it was here. So the curve is getting steeper. It's not constant anymore. See, for the tumble buggy, the delta x over delta t, it was a constant value. The slope on the position time graph did not change. It was consistent. A consistent slope. I guess this way. A consistent slope. No, yeah. This is not a consistent slope. It's a curve. Curves don't have constant slopes. They have changing slopes. And if I draw another one, if I draw another tangent, and I just kind of sketch it like this, maybe about like that. So it looks like it's touching the curve, or could be, if I slide it a little closer, somewhere in that area, maybe up a little higher. So what does that tell you? At that point, further on down, it's even steeper. Notice this tangent line isn't very steep at all. This one, it's getting steeper. And this last one out here, it's getting a lot steeper. So as the curve goes up, it's getting steeper and steeper and steeper as it goes. Now, the question is, and this is assuming you will remember that the steepness of a position time graph, the steepness of this graph tells us what? Velocity. Okay, that's what that's called. That's called velocity. And so if we're saying here the velocity as the go car rolled down the track, okay, as it got further down the track, it was getting faster and faster, as shown by the fact that our steepnesses of the curve, they're getting steeper and steeper and steeper as we go. What does a VT graph look like for that? That's the next question. Well, how do you sketch a, we should draw a motion map first. So a motion map, what does a motion map look like for a go-car that's getting faster? Starts with no velocity at the top of the track, goes down, getting faster as it goes. What does the motion map look like for that kind of motion? Will it have constant length arrows? I hope you're thinking no. The arrows can't be constant length anymore because it's not a constant velocity. It's getting faster. So my arrows are going to start really short because it's not going fast. And then what do? They get longer and longer because it gets faster and faster as time goes on. So for the go-car, it was kind of like this. We started with not very much velocity, and it got faster and faster the longer we went, which means the arrows get longer and longer. And it should be obvious that they're getting longer. That's describing the motion of an object that's getting faster. Now, how much velocity did it have at the beginning? Well, it started from rest, from not moving, which means how much velocity? None, 0. So what I should do here, let me give me an orange here. It starts with no velocity. Because remember, that's 0 velocity. Those are positive. That's negative. So it starts with no velocity, none, and it gets faster positively because it's traveling in the positive direction, because all of the slopes here of these tangents, the slopes of these are positive, which means it's traveling in a positive direction, which is why my arrows are positive. And that means I have to have positive velocities here, but they're getting bigger. The velocities are getting bigger, which means that this graph has to be like this. That graph has to have an up slope on it, okay? Now, one more thing about this. We have not had a VT graph that has a slope yet, and now we see we have a VT graph with a slope. They've all been horizontal. They've been horizontal and above the t-axis for constant positive velocities. They've been on the t-axis for 0 velocities, and they've been below the t-axis but horizontal for constant negative velocity. We haven't seen a velocity that's changing yet, and now we do. Now, how, if you were going to find the slope of this line, you would mark some x's on here, and you would have a rise and you would have a run. And so that little rise right there, that is a change in what? What's changing on the rise? I hope you're thinking that velocity is, and you're right. The velocity is changing for the rise. That's a change in velocity. We would call it, instead of delta x now, we would call it delta v, change in velocity. That means the run part, the run we have, what's changing across the run? Well, it's still time. It's still time on the x-axis. And so that's a delta t. So wait a minute. If you calculate the slope of this, then you're going to take a rise, which is a delta v, over a run, which is a delta t. And what do you have? Well, you have a delta v over a delta t. Now, do you know that has a name? In physics, that has a name. Does anybody know what the name of that is? It's called acceleration. So that's called acceleration. That is acceleration. So just like earlier with the tumble buggy, we had the slope of a position time graph tells us velocity. Well, now the slope of a velocity time graph tells us acceleration. It tells us how much the velocity changes for every one moment in time. Okay? Hopefully I haven't lost anybody yet. So here's the thing. You can't just forget about everything we did. You still have to know that. And now we're adding to it. So you can't just forget what we did and then move on and learn something new. It's continuation of what we had already done. So in class, we talked about this some. Then, one other thing. We need to start adding something to our motion maps now. We need to tell people that there is an acceleration and what direction the acceleration is. Oh my gosh. Well, if you look at this, everybody, the slope of the VT graph, the slope of it is positive. That's a positive slope, which means our acceleration is what? Positive. It's a positive acceleration because we have a positive slope on the VT graph, which means on our motion map, we would actually say this. We would actually sketch an A, and you would point in the positive because the A is a positive acceleration in this case, because the slope of our VT graph is positive, so positive acceleration. Now, in class, what I did was this. I set up a couple scenarios. Now, this is the one from the actual lab. Like, this is what we actually did. Scenario one was the go-car lab. You had a go-car starting at what we would call the zero position, rolling down the track, speeding up as it goes. Now, that's everything we just did. And then I put the go-car on the track. I ran the motion detector, and it gave us graphs, the position time and the velocity time graphs for that motion, which are what we just had on this screen. What the motion detector gave us, it gave us an up curve. Oh no. Oh, I don't know if it's still recording or not, but my computer just froze up. So I don't know if you got all that or if it just froze and I'm frozen on the screen, but I don't know. My computer has been acting up all day. So what the motion detector gave us when we set it up, it gave us an up curve. It gave us a VT graph that had a positive constant slope, and it confirmed what we had supposed was going to be the case. Okay, so I had everybody write this out all together, and so I'm going to just do that. I'm going to use a blue color here, and I'm going to write this out again. This is what we just did. We just did this. We said that the A was positive. We said that this was an up curve with a slope that's getting steeper. We said this starts with no velocity and gets faster. Again, that's zero velocity. Those are positive. That's negative. That's a zero position. Those are positive position. That's a negative position. Then scenario two, and here's where you're going to have to try to make some predictions. I know I'm flying through this. I'm trying to do this quickly. Scenario two was this. I put the go-car at the bottom of the track where the detector was, and I pushed it up the track. I pushed it up the track. So it started going fast, and then it's slowing down as it goes up. So it's going up the track, and it's slowing down as it goes. It's going up the track and slowing down as it goes. Does everybody see what's happening here? Up the track, slowing down as it goes. So you need to think about, okay, what does the motion map look like for that? What would the position time graph look like for that? And what would the velocity time graph look like for that? And here's where I made everyone make a prediction with some pencil. So you may need to pause the video, make yourself a prediction, and then come back, and then you can see what actually happened. So because then we actually did it, the motion detector collected some information, and then it showed us what the graphs looked like. So pause it, try a prediction, come back. Now, here's what's happening. We have the go-car starting fast, and it slows down as it goes up the track. And in fact, it stops at the end. Okay. Now, the position time graph started with a steep positive slope. It started from the zero position with a steep positive slope. And that slope has to get what? Since it's slowing down, that slope has to get less and less. So the curve should actually look like this. It's getting less steep. See, if this was a hill and you were standing on top of the hill, you would say, that's not very steep because you're on the level part at the top. Over here, if you're trying to climb that hill, that's very steep. So I hope you're able to put your mind on that you're starting off really steep. That's fast. And it's getting less steep and less steep and less steep until it finally becomes level, and then there's no velocity. That's what the motion detector showed us. Now, how do you show on the VT graph? How do you show it starts with a large positive velocity and it ends with none? Again, that's a steep positive slope. This is no slope. Like if we were drawing tangents here, the tangents would look like this. That would be a tangent at the beginning. This would be a tangent near the end. That first line, very steep. The second tangent, not very steep at all. It's getting less steep, which means it's getting less fast. So you start positive velocity and pretty big velocity because it's fast. And what happens to the value? It gets less and less and less and less until it gets finally down to zero because it's not going anymore. It stops. I actually stopped the car at the top of the track. So those are what it should look like. Now, last thing, we still have to add our acceleration here. What kind of slope is this on the VT graph? That's a negative slope, which means our acceleration is what? It is a negative acceleration. Negative acceleration, okay? And then we had one more scenario. Last scenario was this one. So now I have the zero is at the bottom of the track, but I started the go car off in a what kind of position? Like where is the go car? That's in a positive position. And it's headed back down the track. So it's going down the track, speeding up toward the zero position. So it's getting faster going down this way. All right. So think about that. We have a go car that's in a positive position away from the zero. It's traveling in a negative direction. It's going toward the zero from the positive side, negative direction, and it's getting faster as it goes. Getting faster. So it starts in a positive position, not moving, getting faster, speeding up as it goes down. So pause the video, try to figure that out, sketch that out, and then come back. So this is what we have. We have the object starting way out here in a positive position, starting with no velocity and getting faster, faster, and faster. Now, how do you sketch that with a position time graph? How do you start with no velocity and a positive position? So positive position, and it's not moving at the beginning. That's up here like this. That's a positive position because it's away from zero on the positive side. And it's going to start with a horizontal type thing because it's not moving. But then it gets faster. So the curve does this. Because that's getting steeper. But it's getting steeper negatively. It's getting steeper negatively. Because the slopes, if you draw tangents on this, that's like no steepness. A tangent over here, that's really steep, but it's negative. Really steep. Let me move that away a little bit. It's really steep, but it's negative. Okay. So that's telling us that the velocity is getting bigger, but it's getting bigger in the negative direction because the line's getting steeper and steeper and steeper with a negative slope. Now, on the VT graph, how do you show that you start with no velocity and it gets faster negatively? That looks like this. Starts with no velocity and it gets, oh my gosh, all these dots everywhere. There's like, oh my gosh. It gets faster negatively. Well, wait a minute, but the line's going down. You're right. It's going further away from the zero. It starts with none and it gets faster negatively, which means this down here, by the time it gets here, that's pretty fast, but it's fast in the negative direction, okay? So that is what the detector showed us when we saw this scenario. Now, what kind of slope is this? That's again a negative slope, which means my acceleration here is a negative acceleration, just like we saw a second ago. So that was the last scenario we did. I know I kind of flew through these. We had a lot more discussion with it in class, but I'm trying to keep this video short. And of course, you didn't get to see the actual graphs that were produced. Well, for instance, for this one, for scenario 3, I believe I still have that one up here. So here's that graph. This is what the position time graph looked like, which is again what we just described here. That's what we showed here. It was sitting at about 1.25 meters away from the 0 position, and I let it go, and you see that this got steeper and steeper and steeper and steeper, and then finally, where did it stop? Oh, look at that. It stopped right at the 0 position. Now, I grabbed it and stopped it, but that's not part of the scenario. I couldn't let it keep going, or it was going to smash into the oh my gosh, easy for me to say, to the detector. Now, the VT graph, this section right here is what we're looking at, maybe. This section right here. Notice, starting with no velocity, and the line goes down away from the 0, okay? Away from the 0, negatively, on the negative side, but further from the 0, which is exactly what we described this as. So that's what we ended up seeing in class. I hope this helps, makes some sense. I was going to assign something. I decided not to. We'll get to it next week. So hope you have a great weekend, and we'll see you. I guess it's not, for all of you, it's not the weekend. Some of you haven't even had this class yet. This won't happen until Monday for the B2 people. So anyway, take care of yourselves. We'll see you next time.